Welcome back, folks. In this part of the tutorial, we will explain techniques that have been used to make permission blockchain more scalable. For those of you who do not know me, I'm Divi Agrawal, and I'm on the Faculty of Computer Science at University of California at Santa Barbara. So before we dive into the scalability solutions for permission blockchains, let us briefly review the overall setting for the permission blockchains itself. So as Amr mentioned in the introduction, the application context that we are considering is really typically involves multiple enterprises, such as those involved in a supply chain application. And the need is that all these entities want to maintain a data infrastructure that can be manipulated and maintained by them collectively. So the challenge here is that even though these entities come together to participate in this particular application, for example, the supply chain application, what they do not have is they do not have the necessary mutual trust where they can grant this capability to one single person or one single entity for maintaining the ownership of this data infrastructure. Okay, so this is where the blockchains come into play. The blockchain provides a guarantee that the data in the block is immutable or is tamper-proof, and that gives a peace of mind, or you can say that they have some trust in the data itself, right? So this gives them the comfort level that they can use a shared infrastructure in which these blockchains will not be tampered with, and each of them can maintain a copy of this data in their own private infrastructure. Now, the flip side of this equation is that in order to kind of maintain this infrastructure, which will make sense to all of them, we have to provide mechanisms that will ensure that these copies of this blockchains that are being maintained by multiple entities are mutually consistent with each other. And the way that mutual consistency comes about is by ensuring that the manipulation operations, or equivalently the transactions, are globally ordered in consistent manner across all entities. And that's where we use this notion of a consensus protocol, and in the context of malicious environment in particular, we use what is referred to as the PBFT, and that was introduced earlier. Okay, so with that background, what we do is we come to the issue of scalability of these infrastructure, and the need for scalability arises because as the number of organizations grow, or even if the number of entities do not grow, what may happen is the number of the transactional needs of each individual entities grows over time, and as a result, what is going to happen is that you want to be able to process larger number of transactions, basically, in the system. And the question is, can permission blockchain be made scalable to process this larger number of transactions in the system? Now, a typical solution for making these infrastructure more scalable is by throwing more resources to the system. And the question is there an inherent limitation in permission blockchains where just adding resources is not going to solve the problem? And that's is what we are going to be looking at during this part of the tutorial. Okay, so with that, so our underlying thesis is that we want to find out if a blockchain system has the ability to process an increasing number of transactions by just adding resources to the system. So before we get into just adding resources, let's see if there are any alternative solutions to this problem. So there are typically two classes of solutions for scalability, and one of them comes about from the area of there is this notion of lightning networks, where basically what they do is they have this notion of building blockchains that reduce the transactional requirement on the main chain, on the blockchain, by offloading the workloads to lower levels. So the idea can be illustrated by using this using this picture. So you can think of that the blockchain itself is really a control plane, okay? And you have the entries in the blockchain are smart contracts, which essentially open what is referred to as a payment channel, private payment channel for interactions among entities in the cryptocurrency context. So what you do is you basically, at some point, you realize that there are two entities who want to interact with each other, and what you do is in the control plane or in the blockchain, you lock the state at a certain point and you open what is referred to as a payment channel. And what then happens is, as these entities who wanted to interact with each other, they interact with each other by doing transactions using this payment channel. And once the interactions are completed, what they can do is they can close the channel, and the modified state can be incorporated into the main blockchain. So this is the idea of Lightning networks, and what you're doing is basically what's happening is you're able to scale the system by kind of partitioning kind of transactions into two categories: the control transactions, which is the locking the state and finalizing the state, or creating these payment channels, and the payment channels are used for performing the local transactions. So next, I would like to examine how we can potentially increase the number of transactions that can be processed by adding more resources to the system. So this is going to be what is referred to an on-chain solution, and it is basically we are going to make modification to the blockchain itself. Okay, so the one way to add resources is by making individual nodes more powerful. So you basically this is referred to as the vertical scaling, and you add more power to each node. But as you know that adding more power has its physical limits. Basically, there is a limit as to how fast the machine can be because of the clock speeds, and similarly there is a limit as to how, even if you increase the network throughput, you still have some limitations on the network latencies. So the vertical techniques only can take you so far. And the other problem with the vertical techniques is that what can happen is, if some of the machines are not as powerful as the more powerful machines, then what happens is the system can operate at the slowest component in the system. So this is the problem with the vertical technique. As a result, at least in databases, the technique that is more used is what is referred to as a horizontal technique. And conceptually, what you can think of it is basically this is the idea of what is referred to as clustering or partitioning, where you essentially try to overcome the scaling problem by doing a divide and conquer. So instead of trying to solve the bigger and bigger problem, you break the problem into smaller pieces and solve it. So that's the idea of what is referred to as the sharding. And what I'm going to do is I'm going to illustrate these ideas based on some of the recent work that has appeared in the context of blockchain, and where the sharding technique has been used. Okay, but before I give you the individual results, what I'm going to do is I'm going to kind of show you as to where the complexity in the system arises in the context of permission blockchain. Okay, so as you know, I think as I've already mentioned, that one of the key component of the permission blockchain solution is that in order to maintain the mutual consistency of the copies of the blockchain that is maintained at different places, you have to make sure that there is global ordering of transactions at all times, and this global ordering component is performed by the global consensus idea. Okay, so when the scale of the system is relatively small, you basically have few number of orders. So for example, here we have 4 nodes. So this is typically a 3f+1 scenario. So that means we can handle up to 1 malicious failure. And what that does is with 4 machines, you can achieve the ordering relatively fast. Okay. In order to scale the system, what you may want to do is you would like to introduce more machines in the ordering capacity. And what that does is, because of the centralized nature of this consensus mechanism, which requires, which is basically, as has been pointed out, is linear to the number of machines that are involved in the consensus, as well as the n-squared messages that are needed for communication. What that does is, by adding more machines, you're going to slow down this component. Okay, and if you add, if you continue on this round, this is not going to work because it's going to become slower and slower. So the idea of sharding is, what you do is you basically break your ordering component into multiple independent pieces, and the notion would be is that you basically shard the blockchain into different categories. So here we have represented by 4 categories, and applications that need to access the blue shard basically have to only do the ordering in the context of the blue orderers, and similarly the greens will go to the green orderers. Okay, so the trade-off is, by partitioning, what you have done is you have made things more scalable, but the sacrifice you have made is that even though you have larger number of machines, the number of failures that you can still tolerate is limited to is limited. So for example, if you had 10 machines, you could handle 3 failures, but if you divide the 10 machines into 3 groups, then you can only handle 1 failure in each group. So that's the trade-off that you have. Okay, and the advantage of this approach is that you can, as long as your interactions or your transactions are within the shard, then they can be done actually concurrently. So you really increase the capacity 4 times in this context. But the challenge that arises is when there are interactions or transactions that have to cross the shard boundary, that are referred to as the cross-shard transactions, then you have to introduce mechanisms so that you make sure that the ordering is consistent across these 2 different shards. Okay, so basically, this is the conceptual problem, and I'm going to now illustrate how the different protocols that have emerged in the last few years and how do they solve these type of challenges. So one of the first one is a VLDB 20 paper, and this is from Mohammad Sadogi and his group at University of California, Davis. And the setting for this is very similar to what I have described, but they motivate the problem of scaling of permission blockchain in the context of geo-replicated setting. So what they point out is when you're dealing with replicated data, and the context of replicated blockchains that are spread across geographical boundaries. What that happens is because the latencies increase as you increase the distance between these copies, and that can give rise to inefficiencies in the system. So what they propose is this idea of what they call a geo PBFT, which basically uses the network topology, and they create these localized clusters which are restricted to a geographical domain which is kind of close to each other, and they execute transactions in the context of these local clusters. So you can think of this is a cluster that you're maintaining in California, and there is this cluster that is being maintained, let's say, in the northeastern part of the United States. Okay, so the malicious, so they run PBFT in a much smaller context, and what they have instead of trying to run a global consensus algorithm, what they claim is that once you have run a PBFT and you have a certified commit achieved at the local level, then what they can do is they can actually, instead of using a Byzantine consensus algorithm across geographic site, they can use something what is referred to as a global sharing, and they theoretically established that all they need is that they need to send kind of F+1 messages during the global sharing phase, and after that the transactions that have been executed in this cluster and transactions that have been executed in this cluster, they are deterministically ordered by all these nodes, and then you go and execute these two transactions. So to summarize, the blockchain is completely kind of replicated at all places. They are not sharding the blockchain. So every machine maintains a complete copy of the blockchain, and what they're doing is they're doing a local kind of consensus on a transaction here, and then global ordering of the locally agreed upon transactions. And once the global ordering has been determined, then these things are executed at each machine to ensure that the mutual consistency of the blockchain is maintained at all copies. Okay. So even though kind of the Sadogi approach or resilient DB approach was partitioning the nodes into different clusters, what it was doing was it was not partitioning the blockchain itself. So the next two protocols that I'm going to introduce, they are going to basically rely on sharding of the blockchain itself. Okay, and once you do the sharding, that has been very effective in the context of database technology. The challenge really comes down to is that when you have interactions that cross the shard boundary, referred to as the cross-shard transactions, they need to be synchronized using some mechanisms. Okay, so there has to be some sort of a coordination. In the context of distributed databases, this coordination happens using two-phase commit protocol, for example. Okay, the first protocol we are going to review in the context of the sharded approaches is what is referred to as AHL, and this is a protocol from, this appeared in Sigma 2019, and it is from Bengchen Hui from National University of Singapore and his research group. So the idea, as I said, is it uses a sharding technique in malicious or untrusted environment. I think that is given for us is that we are dealing with untrusted infrastructure. Now, in order to understand, what the solution strategy that this particular protocol uses, what we should do is we should look at the design objectives that the authors have laid out. So one of the first thing they want is that they want to build a permission blockchain system for network sizes that mirrors the sizes that are being used in the context of cryptocurrency, for example, the Bitcoin and Ethereum, right? The next goal they have is, in contrast to the cryptocurrency, which have very low transaction throughput, what they want to be able to achieve in this environment is they want to achieve a high transaction throughput that is comparable to commercial DBMS technology. So typically this is of the order of 2,000 to 4,000 transactions per second. And finally, they don't want to have a specialized application like a cryptocurrency application where transactions are very, very restricted format. They want to be able to support diverse applications in the context of, in the industries like finance, supply chain management, and healthcare. Okay, so once you laid out the design objectives, immediately the challenges arise. What are the challenges they have to overcome? And this is what the authors kind of outline. So one is, of course, as we have seen, is the one of the biggest challenge or the bottleneck in the context of permission blockchain system is the issue of the consensus protocol, which is based on Byzantine fault tolerance. Okay, so the first thing that they have to deal with is how do you scale the BFT consensus protocol. The second thing, which is right now is going to appear a little mysterious, but they also talk about this kind of the shard configuration or assignment. How do you take your nodes, and how do you do the mapping of the shards to the nodes? Okay, so the challenge there, what they say is that you don't want to run into a situation that a particular shard gets mapped into a node where most of the nodes are malicious. So that's, I think, is another challenge that they have to kind of overcome, and they outline a strategy for that. And finally, because they are dealing with multiple shards, they want to be able to enable kind of distributed transaction synchronization. And the observation there is that you cannot use a single coordinator based strategy, because what happens if that coordinator is malicious? So you have to enable or support distributed transaction in spite of malicious transactions. Okay, so having seen the kind of the design objectives as well as the challenges associated with achieving those design objectives, let's look at the solution outline of AHL, which is referred to as, which is a short form for attested hyperledger. So the first thing is, as we mentioned, one of the first challenges is that how do you scale BFT? So what the authors propose is that they are going to use for each node, they're going to make it into a trusted execution environment using hardware technologies such as Intel SGX, and this is going to be available at every node. And with that trusted execution environment, the authors actually demonstrate that they can run BFT, and instead of needing 3 F+1 F replicas, they only need 2 F+1 replicas, even though they're dealing with malicious failures. So that's, I think, is the first step for scaling BFT. Well, that just by reducing allowing less number of failures, or making the network size smaller with respect to the number of failures, does not solve the problem of the n-squared message cost that is associated with BFT. So the solution they propose is that what we are going to do is we are going to partition the network and the blockchain states into smaller shards. So that way the n-squared cost will be kind of confined to at the shard level. And one observation they make is that when you do this shard assignment to the nodes, what can happen is you can run into a situation where a particular shard is assigned to a node where the failure, kind of the number of failures, malicious failure exceeds the threshold. So that for that they propose a probabilistic assignment which is going to allow them with a very high degree of confidence that such is not going to be the case. Once you do that assignment, basically what you end up with is a setup which looks very similar to what you have in a distributed database setting. So you have these sharded groups or sharded data, and the sharded data is replicated on multiple nodes, and you're going to run BFT consensus because you're dealing with malicious environment within each shard. Okay, so as long as transactions are confined to the shards, then you can execute them locally. Right? Now the issue of transaction management comes into play when you start having cross-shard transactions. So for that, they basically use a coordinator-based approach, which is used in distributed databases in the classical two-phase commit and two-phase locking protocol, except for the difference that they cannot rely on having a single coordinator or centralized coordinator. So the centralized coordinator can be a problem for two reasons. One, it could be a performance bottleneck, and then two, what will happen if that centralized coordinator happens to be a malicious entity. Okay, so what they do is effectively what ends up happening is you basically have this notion of coordination, but the coordination is achieved not by a single node but by a group of nodes that is referred to as a reference committee. Okay, and kind of the regular shards are referred to as a committee, and the rest of the protocol flows exactly the same way as two-phase commit protocol is, that when the transaction commitment is initiated, the reference committee basically goes through and proposes a begin transaction and sends out a prepare messages to these committees, and then once the answer comes back, the reference committee basically goes through a consensus round within itself to agree upon the outcome of the first phase of the transaction, and then it goes to the second round, and then finally comes to the commitment or abortion of the transaction. So that's the outline of the proposal. Okay, so one of the problem with AHL is that it has this notion of coordination that has to happen for all global transactions. So the next result I'm going to present is from a paper in Sigma 21, and this is based on Muhammad Amiri's PhD thesis work, and it's going to be concurrently presented, but I'm going to give you just a high-level overview so that it can be positioned with respect to what we have seen in the context of other protocols. So the goal is similar, that you want to scale the system, and the scaling is going to be dependent upon sharding. You shard the blockchain into multiple pieces, and similarly you partition the network into smaller groups. Okay, the partitioning of the network, you want to do it in the smaller groups is because you want to limit the amount of kind of overhead, or limit the overhead associated with the consensus that has to be achieved among all the network nodes. Okay, so the goal, kind of the main goal of this paper would be is that we want to eliminate the need of coordinator. So you want to basically sort of still support cross-shard transactions, but the cross-shard transaction execution has to be based on sort of the kind of decentralized approach rather than a centralized two-phase commit or centralized coordinator-based approach. Okay, so the observation in our case, in this case, in the case of Sharper, is that we have a predetermined idea that there is this value f, the number of failures, malicious failures in the system. Okay? And typically the assumption is that the number of failures is much, much smaller than the number of available nodes in the system. So if you have that sort of upper bound on the number of failures, what you can do is you can use that information, and based on that you can create these node clusters, which is going to satisfy that every cluster has at least 3f plus 1 if you are dealing with malicious failure. And once you have that, then you know that you will overcome the issue of failures. Okay? So you partition the network into these network clusters, and then you basically also do the same thing with respect to your data. So the data is sharded into these mapped into these clusters. Okay? And now the question is, how is the blockchain ledger maintained? And I'm going to illustrate that in the next. So let's look at what happens, kind of the global view of the blockchain. So this is the starting point, and what you have is basically you are going to, instead of having a linear chain, now you'll have parallel chains in some sense going for each of the shards of the blockchain. Okay, so you have the blue chain, the green chain, the yellow chain, and the red chain. Okay, so if your transactional activity is confined to each shard, then essentially what you have done is you have taken your original kind of the single chain, and you have basically broken it up into 4 different parallel pieces, right? That's what you have done. But in reality, what happens is you cannot be sure that the transactional activity is going to be confined within a single shard. So in order to do that, you want to be able to support cross-shard transaction, and that's what you are seeing. It's being illustrated here in this picture, is that these gray nodes are the cross-shard transactions, and basically the arrows correspond to these cross-shard transactions are interacting with multiple shards. So for example, this particular transaction T12, T22 is dealing with both blue and the green shard, and similarly this transaction is dealing with these transactions. So as a result, the blockchain, the view of the blockchain becomes a directed acyclic graph, where the transactions are not maintained in a total order, but transactions are maintained in a partial order. Okay, and the ordering is determined by the cross-shard activity that is happening here. So for example, here is a transaction which involves all 4 transactions, all 4 shards, and therefore it is ordered with respect to all the activities in the 4 shards. Okay. Now the question is, what does each of the shard maintain? What is the view of each shard? So the global view that is illustrated here is not maintained by any particular site. Instead, each shard maintains its view or its projection of the global view. So for example, on the blue shard, you have these transactions, the blue transactions, in addition, the gray transactions that have been included. So from that sense, if you see, this is basically a permission blockchain in the blue shard area, augmented with these cross shard activity. Okay. So what does, how do we achieve consensus? How do we ensure kind of ordering of these transactions that can be thought of as local and non-local transaction? So what you need is 2 types of consensus mechanism. One is what is referred to as an intra-shard consensus, which is essentially used to order the transactions that are confined within a shard. And this can be, depending upon your failure kind of situation, you can either use if you are confined to the crash-only failures, then you can use a Paxos-like protocol. But if you're dealing with Byzantine failures, then you can use PBFT. So I'm going to assume that we are dealing with PBFT. Okay. The other thing that now is needed is we are going to allow cross-shard transactions to be executed. Okay, when cross-shard transactions are executed, then you have to make sure that these cross-shard transactions are kind of synchronized with respect to the local executions that are happening in the multiple shards that are going on. Okay, so and here again, if we are in the crash-only environment, then you can use a Paxos-like protocol. But if you are using, if you are in a malicious environment, then you will use a PBFT protocol. So I'm going to now illustrate. So I think the intra-shard consensus is really a pluggable protocol that is, you use essentially whatever we have already been using in the past in the context of a permission blockchain. The new thing that we have to devise is these cross-shard consensus protocol. And I'm going to give you a very high-level idea as to how cross-shard consensus is achieved. And so basically, when a client initiates a request for a cross-shard transaction, it goes to kind of one of the leaders of the shard, and that leader of the shard sort of takes over that request and sends the message, the proposed message, to all the sites in both the shards. Okay, and then you have to wait for the necessary F+1 messages from the coordinator or the leader of this who's coordinating the execution of this transaction has to wait for F+1 messages, not only just one set of F+1 messages, but it has to receive F+1 messages from each shard individually. So there have to be F+1 messages coming from here, and similarly F+1 messages coming from here. And as far as the sequence numbering goes, the sequence numbering is initially decided for this shard P1 is decided by the leader here, but for shard P2, each of these are going to send the corresponding number. Okay, and once the execution, once you have received the necessary number of messages, then you can accept the execution and order the transaction accordingly. Okay, so that's what's going to happen is you basically decide on the commitment of the transaction and send out the messages to the necessary number of nodes. Okay, with respect to the Byzantine nodes, it's very similar, where you send out the request to the leader of one of the shards, and the leader of one of the shards coordinates the execution of this transaction on multiple shards by sending out the necessary number of proposed messages, and then you have to wait for accept messages. And here I think the accept messages have to be sent to all the sites. 2 F+1 messages have to be sent, and you wait for 2 F+1 messages from every shard, because you're dealing with, you have to make sure that you don't have any Byzantine behavior. Okay, so that's the difference between the crash only and the Byzantine nodes, that you have to wait for 2 F+1 matching accept messages, and then you have to send out that many messages for the commitment of the transaction. Okay. and once you have achieved that, then basically the transaction is committed. Okay, so the advantage of this protocol is that, one of the things you might notice is that if there is, you basically, one thing you notice that in the context of this particular protocol, the cross-shard transactions are only synchronized with respect to the shards on which they are executing. So if there is another transaction that is executing on a set of disjoint shards, the execution can be done concurrently. So that I think is good, because that you don't have a global bottleneck, meaning that distributed transactions don't have to be synchronized in a centralized manner. Okay, so that's the good side, right? But there is obviously, the good side comes with the bad side, and the bad side is I'm going to just outline the problem and not go into the details. I think I'm going to refer you that the solutions are going to be found in the paper. But the problem is that you could run into, situation where you have, two concurrent execution of two cross-shard transactions, and they both involve they have an intersection of their execution on a particular shard. And what happens is, because we are in an asynchronous environment, what can happen is the order in which the messages arrive from these two transactions, on this cluster, could be different at different nodes. Okay, so because of that, you could have a problem in the following sense, that this particular node might order these two transactions as number 10 and 11, whereas this one might order it in the reverse order. Okay, so the protocol has to make sure that such kind of discrepancies are taken care of, or has to be resolved, and what the way it is handled, it is that whenever there is this conflict that occurs, then it is handled at the leader of that particular shard. So the leader associated with shard P2 is going to make will make a superproposed message, and it is going to resolve these type of conflicts. Okay. Now, in the same vein that what I've described, when you have the situation, what you can also have is that because of this reordering of these messages, you could have a problem of a deadlock. And I'm going to refer to the paper that, so you have to time out, and you have to re-execute the protocol, and so on. Okay, so one of the things that can be done so one of the solutions that is proposed in Sharper is that if you are in a high contention environment, what's going to happen is you are going to routinely get into this conflicting situation that I described in the previous slide. So what they propose is, at the expense, if you know that you are in the high contention environment, okay, where these type of overlaps of this type of conflicts are going to arise frequently. So instead of executing them just using the two-phased approach, what it does is it introduces a kind of an extra phase, which is referred to as a superpropose, where the leaders of all the shards basically go through a coordination process, and using that coordination process, they come up with some understanding as to how these transactions have to be ordered, and then proceed with the regular flow of the transaction execution. So this is, there is a trade-off. You introduce more latency, but then you reduce the amount of conflicts and corrections that have to happen in the system. Okay, so this, I think, should give you an idea of what is happening and how sharding and partitioning of the network is being used. So let me summarize our discussion on scalability. We saw various approaches for making permissioned blockchain systems scalable. And the first approach, what it did was it basically partitioned the network into smaller clusters, but maintained a centralized or a single ledger across all the sites. And with that, what we were able to do was the consensus was carried out in a localized context, and then you could do the replication of the ledgers or transactions across the global all the global cluster using a replication technique. Clearly, maintaining a single ledger is not, that does have its own limitation, and that was exploited in the technique that I presented as the AHL technique. And here, what you did was not only you partition the network, you also partition or sharded the ledger itself into different clusters. So there was a mapping of the shards to the cluster that was maintained. And in this context, if your transactions are confined within a cluster, then you could, you don't need any you can scale the system. However, what we found was whenever you have a cross-shard interactions and you're bound to have that kind of interaction, then you need to do some sort of a coordination across different clusters. And the AHL approach in this context uses a coordinator-based approach, which is very similar to what we know as two-phase commit in distributed databases, with a main distinction that instead of having a single node serving as a coordinator, they actually have to use a notion of a reference committee that would serve as a coordinator. And the reason you need to use a reference committee is because we are dealing with malicious environment. So one of the problem with one of the drawbacks with the AHL is that what can happen is as soon as you have any amount of cross-shard activity, you have to have this centralized coordination that has to happen through the reference committee. Sharper, as we saw, what it does is it basically kind of eliminates the centralized coordination, and it only requires coordination among the clusters on which the transaction was involved. So that, I think, reduces the synchronization requirement significantly, because you could now allow multiple cross-shard transactions to be processed in parallel in the system. So this, this basically, this is generally these are the flavors of the algorithms. One of the problems with the flattened approach is if the clusters are far apart, then you are going to achieving cross-shard consensus is going to incur in high latency. So with that, I am going to close this part of the tutorial and will open to question and answers session. And hopefully, if there are things that were not clear from the recorded portion of this talk, then we can take it in Q&A, and we will try to answer those questions. Thank you.